Welcome to the class. This class is dedicated towards intake and nozzle of an aircraft engine. We know that the aircraft engines are either of turboprop, turbojet or maybe ramjet and turbofan type. But in either this turbo or ramjet kind aircrafts, we will have an intake and then there is a nozzle. So this nozzle we are interested to study along with intake in this class, how to quantify the performance and how to understand the flow and how to associate it with the corresponding performance parameter. So this is what the objective of today's class. So here first we know that there is suppose an engine and that engine has the components which includes aircraft intake for the engine, and then after the intake there will be compressor, and then after the compressor there will be combustion chamber, and then after the combustion chamber there is turbine, and then there is nozzle. So these are the components of an aircraft engine. So if I feel that this is the compressor, if this is the compressor of the engine, then what will happen? Air will try to come towards the compressor of the engine, where we will see that this is the section in which atmospheric conditions are there, and then after passing through this passage, which we are calling it as intake, it would reach condition which is 1. After the end of compressor it would reach conditions which are 2, and then after having compressor we have a turbine, in case of turbine it will enter. Before turbine we have combustion chamber. In the combustion chamber fluid would enter at state 3 and leave at state 3. For the combustion chamber entry state is state 2 and the state at the exit is state 3, and then we have turbine where entry state is 3 and then exit state is state 4. Having said this, after this turbine flow enters into the nozzle and then at the exit it has state 5. So these are different components of the aircraft engine which are known to us. Now our focus at this moment is on intake and nozzle. So our focus is on this component and is on this component. So practically we will see about intake to start with. As I said, intake is practically a diffuser, and the job of intake is to increase the pressure while flowing through the duct, and then it will supply that high pressure air to the entry to the compressor. So this is the primary job of an intake, but we have to reduce the losses which are related to loss of pressure, loss of total pressure in the intake, and then intake should be properly aligned such that it should be having highest performance at different angles of attacks, and it should have highest performance at various operating conditions like maximum thrust, low speed and high speed. So for that the intake should always supply given mass flow rate of air with designed pressure or a required pressure to the compressor. Then there are different types of intakes. We can have an intake which is like S bend. So this is an S bend intake, This is also termed as a buried intake, and in this intake we will have engine buried inside the intake passage, and then this is the engine. So flow will come like this. So center line of the intake has change in geometry. So this is a S bend intake, and then there is straight through intake. In case of straight through intake, we have engine at the end of the intake passage, and then this engine is placed somewhere the control surfaces of the aircraft. So this is a straight through intake. So there are different ways by which we can design an intake passage. So intake passage can in general be a rectangular duct where we have a two-dimensional duct, which is a rectangular duct like this, where this duct would act as a diffuser. So this is inlet, this is outlet. So this is 2D rectangular intake. Or intake can be conical, where it will have a cone shape, where this will be the entry and this is outlet. Or there can be intake which is annular intake. So this cone would have a passage which is an annular passage, and flow is going from the annular passage and then doing the necessary pressure rise. So this is annular intake. So intake in general might have different shapes. So sometimes sometimes there might be change in geometrical shape, along the center line, or there might be change in the slope of the center line itself. So there are some intakes which are hidden or buried intakes, and these intakes, hidden or buried intakes, are having advantage or potential of masking the radar reflections of the engine face. Means these intakes can hide the engine from the radar. So the presence of the engine will not be felt. So that will also be one of the assignments for the intake. Apart from this, these intakes whatever we have studied, they have one kind of cross section at the inlet and the same kind of cross section at the outlet, but then there can be an intake which would have different cross section at the inlet and different cross section at the outlet, and then this might be due to the optimization or might be due to the requirement for connection. So, there is a rectangular shape at the inlet and then this shape transforms to the circular shape at the outlet. So, this is rectangular to circular or rectangular to elliptical shape transformation type of intake. So, such intakes are also designed, and all these shapes are practically dependent upon the given speed range of the aircraft or flow regime of the aircraft. So, aircraft which if it is in subsonic, then there are different kinds of intakes and different kinds of shapes, and then if it is supersonic, then it will be a different kind. But these are general guidelines or general shapes which are followed for the aircraft. Now, suppose we have an intake and then that intake, how does the flow through the intake would change in case of different conditions, and then how mass flow rate would alter, that is what we are going to see here. So, this is the intake suppose, and then in case of high speed we will have flow through the intake like this. So, this is flow through the intake in case of high speed. Since the captured stream tube area, which is suppose atmospheric AA, is less than A1 or maybe A2 in this section, then this is leading to low mass flow rate. So, a streamline is approaching the intake, and then we are considering a streamline which will hit the lip of the intake, and then this is the minimum area of the between the two streamlines which are hitting the lip, and so this area we are calling it as captured stream tube area, and this area is minimum. So, this is leading to lower mass flow rate, and then what would happen in this case, we are having a divergence from here A station A to 1, station A to 1, and then again there is divergence from 1 to 2. So, if we plot TS diagram, then we can see that at station 1 there is, at station A this is the pressure which is PA, and then from A to 1 there is rise in pressure. So, 1 is here, so this is PA, this is P1, and then from 1 to 2 ideally it would have gone like this in case of ideal, where we expect the flow to be isentropic, we expect the flow to be adiabatic and reversible. So, this would have been P01, but what would happen in reality is we would not reach to the state and we will reach here. So, this is 2, and since it is 2, so we will reach here, which is 2. At 2, if we go isentropically towards total conditions, then we will be at P02. So, this is P02, this would have been P01. So, this is the loss in total pressure at the intake. delta P naught in the intake, but we should note here that the total temperature is same. So, T naught 1 is equal to T naught 2 since flow is adiabatic in the intake, but there is delta P naught in the intake, and that is P naught 1 minus P naught 2. So, there is loss in total pressure in the intake, and then this rise in pressure from A to 1 is external compression, and then this 1 to 2 is internal compression. Now, this is what we discussed for high speed and low mass flow rate intakes. Now, when it is working with low speed, then the streamline pattern will be different, and approaching streamline will approach like this. So, there is little acceleration at the entry. So, we would have captured more area at station A than the face area of the intake at station 1. So, if we try to plot the TS diagram, then we are here at station A, and then we will say that it is PA, but P1 has lower pressure, then this is A to 1. So, there is expansion in the process A to 1, velocity will increase, and then 1 to 2. Is this process 1 to 2. In reality we would reach 2, but if we would have followed the isentropic path, then we would have reached this as P naught 1, and now we would have reached P naught 2 here, but both would have same total temperature. So, this is P2, P naught 2 and P naught 1, and both the kind of flows would have same things, like there will be delta P naught, which is total pressure loss. There is same total temperature as of the inlet of the intake to the exit of the intake, but the second option is for low mass flow rate, low speed and high mass flow rate. So, these are the flow patterns in the intake which are telling us how would be the streamlines around the intake. So, now we will move and then see how we can have the variations in the said thing, which is external and internal compression. So, this is what our intake, and this is suppose a turbofan composition where we have a fan now. The flow is approaching the intake, and then this is the inlet section of the intake. Then we have V naught, A naught, M naught and P naught are the pressures at the naught condition, which is atmospheric conditions 0, and this is 1 and this is 2. So, if we plot the variation as what we said. Then from 1 to 0 to 1 we have increase in pressure and decrease in Mach number. So, we have increase in pressure. Further, there is increase in pressure, but at different rate for 1 to 2 section, which is entry to the fan. Similarly, in case of, this is for pressure. Similarly, in case of Mach number, this is x, Mach number is decreasing till section 1, and then there is further decrement in Mach number till the section 2. So, this is Mach number. So, this is how we will have external compression and internal compression for the intake, and this is what the captured stream tube area. We can know that the area Mach number relation, and then we can write down the expression for E naught upon A is equal to M1 upon M naught into 1 plus gamma minus 1 by 2 M naught square divided by 1 plus gamma minus 1 by 2 M1 square bracket raised to gamma plus 1 upon 2 minus gamma minus 1. This is the relation between the captured stream tube area and the inlet area of the intake. This is the flight Mach number and this is the Mach number at the inlet. So, this we can plot where we have A naught upon A1 and M1 on the x axis, this graph would look like this, where we have increasing M naught in this direction, where M naught 1, M naught 2, M naught 3 will take place. So, this is how, if for a given M naught, which is free stream Mach number, and given M1, if we have this much area ratio for A naught upon A1, that is for given A1, we will get this much of A naught. Now, if we increase the free stream Mach number, then we will get more captured free stream area or more captured stream tube area. This is how we will interpret this curve. Having said this, this is for internal and external compression, and we see that there is one curve or bluntness to the intake, and then that bluntness leads to expansion of the flow at the intake. So, this M1 would have been the area, M1 would have been the Mach number in this location, which is 1. Now, beyond that there is decrement in cross section. So, flow will accelerate, and then we can feel that the Mach number profile will be like this, where flow has accelerated to high Mach numbers till certain extent, and then that high Mach number is Mach number max, and we expect it to be lower than 1. But suppose at this minimum cross section or throat, if we find out what is the mass flow averaged Mach number, then that is M throat, which is mass flow averaged, and our expectation is that with this contraction which is acting as nozzle, M throat should always be less than 0.75, such that flow should not encounter any supersonic pockets in the intake. This is leading to an expression which is highlight, which is the area of the inlet of the intake, which is also called as highlight, divided by A throat is equal to A1 divided by A throat is equal to M throat divided by M1, 1 plus gamma minus 1 by 2 into M1 square, 1 plus gamma minus 1 by 2 into M2 square, bracket raised to gamma plus 1 upon 2 into gamma minus 1. So, for a given composition or given highlight area to a throat area, which where both are known to us, if we plot them with different M1, then this is the variation for given M throat Mach number. So, if highlight area, which is this A1, to the throat area, if we increase, then throat Mach number will increase. If we decrease, then throat Mach number will decrease if we increase the Mach number M1, and then this graph would have M throat 1, M throat 2, and in this direction M throat increases. So, for a given Mach number, we will have this as the ratio of highlight area to M throat area for given M throat Mach number, but that area ratio will increase for the increment in M throat Mach number. This is what the interpretation of this curve is. Having said this, we have to take care for the bluntness, so that it should not have led to the supersonic flow in the intake. Then we can see that the same intake would have different flow pattern depending upon the angle of attack, and we have seen that this is the flow pattern when we have intake perfectly aligned with the velocity vector. But now, if intake is not aligned with the velocity vector, we can plot the curve, and it would look like this. And flow is coming like this, due to which we have a big separation here in this region, which would lead to lower mass flow rate. So, intake should be properly designed to cater a range of angle of attack. Having said this, we will move towards the supersonic intakes. Supersonic intakes can have different types, and they can be either internal compression, external compression, or mixed compression. So, external compression intakes will be composed of different ramps. We know that supersonic flow means flow with Mach number more than 1. So, if Mach number is more than 1, then we will have shock when flow turns into itself. So, there will be one ramp which would create one shock, and that shock is this. There is second ramp, so this will create second shock. There is a third ramp which will create third shock, and then we expect all the shocks to meet at a location which we are calling it as cowl, and this location is lip of the cowl. So, flow while passing will get turned accordingly, and then it will become parallel to the wall. So, this is external compression intake for supersonic aircrafts. Now, there can be internal compression intake, and then there can be mixed compression intake. So, mixed compression intake would have both external compression due to the shock, and then there is a duct in which rest of the compression would take place due to the shape and hence associated shock structure. So, this is the aircraft. So, there will be a shock which is originated from the lip or from the point, and then this shock will reflect inside. So, due to the first shock there will be compression which is external, and due to internal shocks there will be compression which is internal to the duct. So, this is a mixed intake. Then we would have these all shocks are having certain angle which is lower than 90 with the velocity vector. So, those all are oblique shocks. Hence, there is a different type of intake which can have normal shock at the inlet, and this normal shock inlet is a special. So, this is normal shock intake, where major pressure rise in static case would happen with the shock, and then corresponding total pressure loss would also happen with the shock, and rest of the pressure rise will take place in the diffuser or intake. There are different normal shock position conditions. So, if normal shock is present in the intake before the entry, then this is called as subcritical operation or subcritical mode of operation. In this case, flow will approach, and then there is some spillage where lesser mass flow will go through the intake. So, here we have normal shock. Highlights are normal shock which is sitting away from inlet. This will happen due to higher back pressure. Back pressure means pressure inside the engine, and then this leads to lower mass flow rate. Now, this shock can be adjusted perfectly at the inlet like this. In that case, no spillage will take place and maximum mass flow rate will happen, but this is at the lower engine operating pressure. So, this is at lower back pressure, and this operation is called as critical mode of operation, and this has higher m dot. Now, there is third mode of operation where we would have the same shock which is exactly at the inlet would happen inside the intake, and in this case there will be an external shock which is appearing at the top, and then there is an internal shock. This shock structure at the wall would vary for the viscous flow, since there is shock wave and boundary layer interaction. So, flow will approach, and then this is called as supercritical mode of operation of the intake. Here we get higher mass flow rate, and this is with further lower back pressure. So these are the different modes of operation of the normal shock based supersonic intake. Now we will find out the intake efficiency formula, where suppose we have this condition which is atmospheric at the inlet and then this at the exit of the intake. So this condition is 1. Then we will define isentropic efficiency of the intake, which is isentropic efficiency which is defined as T naught 1 dash minus Ta divided by T naught 1 minus Ta. So this is basically related with the conversion of kinetic energy into the pressure rise in ideal case, and this is conversion of kinetic energy into the pressure rise in real case. So this is coming as the difference between total and static temperature in ideal case and total and static temperature in the real case. This can be well understood if we plot the TS diagram for the intake. So this is T and S axis. So we are here at state A. So we are here at PA. At PA we have total pressure which is P naught A. Okay, but in the process of diffusion we will reach P1, and then at this is the static pressure rise in the process of diffusion in the diffuser or in the intake. So there will be total pressure which is P naught 1 in the exit of the intake, but since the process is adiabatic, both will have same temperature, which is T naught A is equal to T naught 1. So this is the case which we would have. So this is A, this is 1, this is not 1, this is not A. But if isentropically we would have done, then we would have reached P naught 1 pressure at lower total temperature, which is T naught 1 dash. This is what the total temperature we would have reached at the P naught 1 pressure. So we can write down this formula as T naught 1 dash minus Ta is equal to efficiency into Ca square divided by twice Cp. Since basically we have from this formula we have isentropic efficiency as ratio of two temperature difference, where we are taking numerator as it is on left hand side and denominator we are multiplying by isentropic efficiency. So we have denominator T naught 1 minus Ta, but we know T naught is equal to, we know the steady state energy equation, which is H naught is equal to H plus C square by 2 or V square by 2. So we can write it as T naught is equal to T plus C square by 2 Cp. So we have T naught minus T is C square upon 2 Cp. So this we can make use, and we can write down this as isentropic efficiency into Ca square divided by twice Cp. So having said this, we can further use this for finding out the rest of the relations, where we can write down P naught 1 upon PA, P naught 1 upon PA is equal to T naught 1, P naught 1 upon PA is here. We are saying P naught 1 pressure ideally would have reached T naught 1 dash as temperature. So, T naught 1 dash upon Ta bracket raised to gamma upon gamma minus 1. So, this expression can be written as T minus T naught 1 dash minus Ta upon Ta. So, this is just a rearrangement, bracket raised to gamma upon gamma minus 1, and this rearrangement helps us to give this T naught 1 dash minus Ta in terms of efficiency. So, we get P naught 1 upon Pa is equal to 1 minus isentropic efficiency into Ca square upon twice Cp Ta. But we know that Cp can be written as gamma r upon gamma minus 1. So, this we can write as 1 minus isentropic efficiency into gamma minus 1 by 2 into Ca square divided by gamma r Ta, and this Ca square divided by gamma r Ta is practically Ma square bracket raised to gamma upon gamma minus 1. So, this is how we can find out what is the total pressure at the exit of the intake. So, we know static pressure at the inlet of the intake, we know Ma, and then knowing the isentropic efficiency we can find out P naught 1, which is exit total pressure at the intake, and this is the formula. But we know that T naught 1 upon Ta, process being adiabatic, is 1 plus gamma minus 1 by 2 Ma square, which is valid since process is adiabatic. For total conditions we need reversibility, but for total temperature we do not need reversibility. Further, having said this, we need to define one more efficiency for intake, which is said as RAM efficiency, and RAM efficiency is defined as defined on the basis of actually pressure rise P naught 1 minus Pa, which is actual maximum pressure rise divided by ideal maximum pressure rise. We would have gone from Pa to P naught 1, which is maximum pressure rise in actual case, and ideally we would have reached from Pa to P naught A. From Pa we reached to P naught A, P naught 1, but ideally we would have reached Pa to P naught A. So, this is what the definition of RAM efficiency is. So, RAM efficiency can again be said P naught 1 upon Pa minus 1 P naught A upon Pa minus 1. Here we know that P naught A upon Pa is 1 plus gamma minus 1 by 2 m square Ma square bracket raised to gamma upon gamma minus 1. Practically speaking, the RAM efficiency or isentropic efficiency, also termed as diffuser efficiency, are same and they are interchangeable. These efficiencies are more used for subsonic intakes. In case of supersonic intakes, total pressure ratio or pressure recovery factor is said to be important. with this we end the discussion about the intake, and then we will use this discussion on intake or these formulations for intake for the calculations, where we have to do calculations for the turbojet, turboprop or turbofan kind of engines, or also maybe in the examples. Thank you.